Thank you, Randy. Welcome, everybody. Today, my presentation is on Vibroacoustic as a fast diagnostic tool for on-load tap changers. So the first part of this presentation shows how Vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers online or offline before they create an outage. And the second part will present a real case showing how New Brunswick Power has used this tool to adjust properly an OLTC. So 40 to 50% of failures on transformers come from tap changers and are of mechanical origin. 4 studies done by Hydro-Quebec, ESCOM, CAA, Australia for 10 years on 3 continents shows the same results, and CGRE and IEEE confirm. For example, here you see in orange, the value for Hydro-Quebec is 45%. So what are the existing methods for OLTC testing? So this table shows a brief comparison between the 5 existing methods available today. Vibroacoustic method offers the widest detection spectrum, and this table is from CGRE. For example, you can see that overheating and cocking, here you can see overheating and cocking is marked low for vibroacoustic, but is marked excellent for timing transition and arcing. Why it's low? Because as soon as you have a vibroacoustic, you need absolutely an impact, you need some noise. And here on this table, I recommend really to analyze this table carefully. You have the problems are shown, and here for each method, you can see the efficiency of each one. What kind of benefits OLTC's vibroacoustic testing bring to electric utilities? A total of 14 benefits have been identified. Applicable to any kind of tap changers, applicable online or offline, quick, easy, and intuitive tests similar to a stethoscope, and with vibration and current combined, we are able to detect a large range of potential problems. Thanks to this method, we have a better understanding on how the tap changer works. Thanks to this understanding, we can detect problems at earlier stage, and it's excellent in terms of timing and mechanical adjustment. And it's an easy tool to detect arcing contact problems, of course, online only. And we have a powerful software analysis thanks to Hydro-Quebec envelopes, and a high sampling time and unlimited recording time unique in the market. It's an excellent tool to help the user to decide which OLTCs are due for a maintenance operation. And in testing OLTCs before and after maintenance, this tool can be used for quality control. And in testing year after year, trending analysis becomes easy and allows reduction of maintenance interventions. And our goal is to reduce the transformer failures, of course. So typically, the transition of the diverter switch is done in only 50 milliseconds to avoid overheating the resistance. And we are able to listen all the impacts of the mechanism during a step-up or a step-down operation, and the motor operates between 2 to 12 seconds. Here you have an example for a resistive OLTC type. The diverter switch operation sequence is moving in this schematic from tap 3 to tap 4. And here we show exactly how this works. Motor drive. So this motor allows the tap changer to move from a position to another. And in recording and analyzing the EC or DC current of this motor during the step up or step down operation, we are able to know if the mechanism are forcing or not. And the motor current allows us also to start and stop the recording. So this way we can focus only the event. Vibroacoustic diagnostic principle. Each operation of any on-load tap changer produces a specific vibroacoustic wave pattern or a signature or fingerprint. And with a vibroacoustic sensor, which is an accelerometer, we can record the signal the same way a stethoscope picks up a person's heartbeat. And a stable OLTC always shows consistent signatures. Any degradation of the OLTC induces changes in the signature. So how we do these measurements? So we have to be careful about the sampling time, which is the time interval between two recordings. So this parameter, we need absolutely to keep it in mind. And the magic value is 10 microseconds, which is the sampling time, or which is exactly the same frequency of 100 kilohertz. In this slide, you can see an example of a good and bad recording vibration signals. So this is an example of vibration of a ball bouncing on a plate. Here you have a 10 microsecond sampling time, which is absolutely required for vibration. So you can see the signal here. Exactly the same vibration, the same impact, but recorded at 100 microseconds. So this kind of value are good for timing motion, for example, for breakers. And here it's just to show the quality of the signal at sampling time 500 milliseconds, and you will see a totally broken signal. And now the next slide will show the zoom of each part of each signal. So here you have at the 10 microsecond, you have a clean signal, very smooth. And so we miss nothing. At 100, the signal starts to become broken. And at 500, well, it's absolutely nothing. You just get, it's not a signal. So what we need an AC current clamp or a DC current clamp, the accelerometers, and one usually is enough. And of course, you need the TAP 4 or TAP 4 Plus. This is our instrument, which is a software driven. And here you have all the technical specifications of what I told you in the previous slides. So here you have some examples of connections. So what you need, of course, we need first the tap glue, because we glue this tap base, this mechanical stud on the transformer on the side, or it depends. This is we need some experience where to install this accelerometer. It's exactly like a stethoscope. You are not going to put it in the arm or in your hand. You are going to put it close to the heart. And then after the accelerometers, there's some specific cable. We call it a microdot, and typically a BNC cable is used. And exactly the same for the current, for the motor current, which if the motor drive is on EC, so we use this clamp. If it's a DC, we use a DC fluke clamp. And the instrument is driven by the computer through the USB cable. And we have another instrument, well, which is a recording event, which is the standalone instrument, exactly the same like the previous one. Here it's first step, we need to identify the tap changer, so the motor drive mechanism in the control cabinet. Well, I'm not going to show the video, but just you need to identify these parts. After here, you can see second step, the accelerometer should be installed at the closest possible location to the transition mechanism. Here you can see the aluminum base on the left, which is glued at the best location here. Then the accelerometer is screwed in that base. So it's exactly what we do. And for your information, this aluminum base stays there for 1 year, 2 years, 3 years, 10 years. We do not remove it, because this way, the next time we come to do a recording, we have nothing to do, just screw the accelerometer at the same location. Here are some examples of accelerometers installation. Some examples of current clamp installation. This one is really simple because the motor drive is easily accessible. And sometimes it's you need absolutely to have the schematic because you don't have access to the motor drive because it's hidden in the control cabinet. So for online tests, presence of high voltage, we record operations of a 1 or 2 taps step up and step down of 1 or 2 taps, and tests are performed in such a way to minimize the impact on the consumers. And for offline tests, we record all taps to get a reference. So here you see an examples of raw data, like in blue, light blue, and what we call the envelope, which is calculated and which has been patented by Hydro-Quebec in 2001. Here you can see in red. And from these envelope, what we extract, we call it these Hydro-Quebec envelopes. We get a low, high frequency envelope and low frequency envelope. And here you can see the envelope of the current. And so why envelopes? It's in fact to simplify the signal, to get the shape of the signal, and to focus on valuable impacts only, and easy to analyze and easy to compare. For example, if you can see like the Vibroacoustic, if you compare this envelope to what your eye see naturally, it's exactly the same. So the envelope, it's something which helps the analyze of the signal, because the Vibroacoustic, as you can see, signal is really a lot of spikes, a lot of informations, but so the analysis is not easy. So impacts in the standing and text on the envelope. So this is the hardest part of the Vibroacoustic. We call it the Vibroacoustic interpretation. So every tap changer has a specific sequence of operations that can be identified in the envelopes. And depending on the model of OLTC, different signatures can be obtained, which are characterized by specific operation length that you can see here with the motor, the number of peaks that you can see, for example, a diverter switch once impacts, and the second impacts in this specific sequence, and the shape of the current, which is you see here in the blue, amplitude of the impacts. So here you have the amplitude of the impacts. So this is a good information, and so on. So the sequence of operations associated with an OLTC is described in the operation guide provided by the OLTC manufacturer. Here, it's a diagnosis can be made in 15 minutes for an online test and 1 hour for an offline test. Here you see what we get as a raw data. You have for example, here it's an EC current for a motor drive, and here you have the impact of the diverter switch. So from this, immediately the software calculates the envelope, the Hydro-Quebec envelopes. Here you can see the motor current, the high frequency envelope, and the low frequency envelope, and the Excel reports. With the Excel reports, when you have a dark blue, means that you need some specific attention. And after, we have an off-site deep analysis, which can take a lot of hours of analysis, usually 3 hours, and where you analyze the Excel reports, exactly the same that you get in the field. You can analyze also, get information on the contact square, thanks to the high frequency envelope and low frequency envelope. You analyze the envelopes. For example, here you have a current which shows like an over value here. So this means that the motor is forcing. And we have also diagnostic cards. We have developed a Zensol database where we get our OLTC reference signatures. Here it's an example of wear contacts just to show that the high frequency and low frequency envelope are really useful. Before the intervention, more than 60% of difference between the high and low frequencies that you can see here. Here it's the low frequency, and here it's a high frequency. So you get a difference in their amplitude. And after repair, after the intervention, less than 20% of difference between the high and low frequencies. So in fact, before we do not open anything, and already we have a good information on the contact wear of the tap changers. Here it's really easy to find it's just an immediate analysis. It's an example of poor lubrication. It's a high torque. This unusual part shown on the curve means that the motor is forcing. And here it's also something very easy to detect. It's an example of asynchronism. Here you can see that 120 milliseconds daily after the end of the current envelope. These test results show an example of asynchronism of the switching operation. In normal condition, the switching operation should occur before the current stops flowing in the motor. That's, you can see here clearly. In the case illustrated on the left, the switching operation signal is delayed by 120 milliseconds after the end of the current. When we zoom here, we can measure this delay. As it can be easily observed, this kind of issue doesn't require the use of a reference signature, and the asynchronism can be detected immediately. And the intervention in this case consisted in uncoupling the drive motor and adjusting it so that the switching operation could occur before the motor current drop. And the figure on the right represents the normal condition of the mechanism after the repair. In this picture, it's an example of arcing. In this picture, an example of arcing contact is presented. Two tests have been performed on the tap number 10 of the same OLTC. One test has been performed on offline, the red curve on the bottom, and the other one online, the black curve. By comparing the two signatures, a big difference in the maximum amplitude can be easily observed. In fact, the maximum amplitude of the offline test is 8G, while the one of the online test is 35G. And the image on the right shows the superposition of the two signatures through which is possible to observe the presence of an extra peak in the online test. And this extra peak represents the arcing contact phenomenon. Here, this is the harder pass. It's an example of impacts and timing association. So it's why here you have the Vibroacoustic, the zoom of the impact, and this one is associated to the timing transition of the diverter switch. So this association is generally hard, and it's why we have developed the impact association with the dynamic resistance measurement. So this way, this part is really easy to do thanks to the three signals that you will see in the next slides. The abnormal inrush current is really easy to detect. Here you have a good one and a bad one, and the one on with the green curve has been observed. It was in fact bad timing down in the control cabinet for the tap changer. So it was totally new transformer with an LTC installed. It was in Alberta. So the same here. Here you have, thanks to the software, here is an example of motor drive current analysis throughout the years. So one is done in 2014, the other one in 2016. And we can notice some malfunction, sorry. And are other examples of inconsistent setup connections. So just you put the signals year after year, and you can see how you can see the trending of the signals. The analysis of the braking mechanism is an important part of evaluating the health of an OLTC. And this is done by observing the appropriate portion of the recorded current and the corresponding vibration measures by the accelerometers. Other relevant information should be sourced from the manufacturer manual. So always you need absolutely to have to collect some informations, so some manuals. So this way you can do the good association with the vibroacoustic and the motor current. It's why on the first one of the first slides we were talking about what kind of benefits. So and I have written it forces you to understand how your mechanism work thanks to the impact. It's exactly when you drive your car and you get some noise and you record this noise. This noise is normal, and one day you get some bad noise impacts coming from the front wheels. So at this time you just go immediately to the garage to understand what is happening. So it's exactly the same. So the challenge, how to facilitate the compression of vibroacoustic signature. So several mechanisms are operating at the same time. So one way to address this challenge is to analyze simultaneously three recordings: the vibration, the dynamic resistance, DRM, and the motor current of the tap changer in action. So what we need what we call a tap 4 plus. It was like the new generation of the previous instrument whose name was tap 4. And typically we have also, this accessory that we call tap DRM, dynamic resistance, which is in fact a current source. And of course, the tap changer must be offline. Here, I hope that you are familiar with these curves of the DRM recordings. Just here you move from 12 to 12A. And here you have a lot of operations recorded at the same time with the tap 4 plus. And here you can see the contact while they move. You can see the correlation between the electric schematic and the mechanical movement. So this, I'm going to do it. So I go back just to show you how this works. And at the same time, we get the impacts and we get the DRM signal and the current. So this is the electric association with the mechanical part. So this is what we get. We get the dynamic resistance curve, the vibration, and the motor current. So the association, the correlation between the impact and the transition for the diverter switch is really easy to do because you just have to see it. You have nothing to guess, because when you have only the motor current and the impact, you must try to guess which impact is the good one. So with the DRM, so the first step is to learn how the tap changer is working in putting the motor current, the vibration, and the dynamic resistance. And the next step, when you are online, of course, you don't have the dynamic resistance signal, but you know, thanks to the offline to your reference test, you know what this means exactly. So after, it's easy to compare with like online signal with an offline signal. So here it's with a high-speed camera also, just to show the correlation between the dynamic and the vibroacoustic. So here each impact is showing like what how the mechanical movement is occurring. Here are some examples of recording for different tap changes done with the tap 4 and tap DRM for MR or ABB. Here we have some examples of recording done with the Hydro-Quebec. So you have the tap DRM, the tap 4 plus, the current clap, which is now here, it's an EC. It's here we have done like it's just to show which wire has been used for the recording, because in the previous recording we have noticed that sometimes people change the wires and then after they get different recordings. So it's for the motor current. So it's really hard after to do like the comparison between two tests. So it's important that it has to be at the same wires and the same location for the accelerometer. It's why we need to always have the aluminum base put exactly at the same spot and the transfer connection. So this is here an example of a typical recording. Looking at the image on the left, the total operations time shows 6 seconds in the bottom left. Here you have the motor current. Looking at the image on the right, the resistant transition and the corresponding current drop are highlighted. Here you have the resistance transition. And we can also see the vibroacoustic signals of the diverter shown by the accelerometer's curve that you can see here. So after when you zoom all these signals, so you know exactly that this impact is the good impact and it's a right one, because sometimes you could have record some other impacts of contactors working on the control cabinet. So it's just disturbs our analysis. Here it's an example of a special test done between tap 8 to 10 and 10 to 8. Just shown are several step up and step down operations recorded in a single test. Look at the arrows showing that voltage or current are not interrupted, because the client was suspecting that something was wrong during the transition. And such tests are performed for tap position, where we suspect that there might be a problem. We go up and down this tap position to gather data to troubleshoot the problem. And we have repeated this several times just to be sure that everything was correct. And here it's when the DRM, the vibroacoustic, and the motor current. So we have a software to be able to analyze all this very easily. Here it's exactly the same than the previous slide, but with the zoom. So each time when you have a transition here, you can see the impact happening. So an example of action plan to elaborate a predictive maintenance for transformers with OLTC. Step 1, establish your transformers list with OLTC to monitor. Step 2, for each transformer, do a complete test to get a reference all taps offline, tap plus and tap DRM, and we have developed a checklist. Step 3, produce a complete report analysis for each OLTC transformer. So we have developed also Zensol template report analysis. And so I can guarantee that at the end of this report, you will understand exactly how your tap changer is operating. And step 4, according to diagnostic results, you can establish your maintenance plan for each transformer. Because thanks to this report, you will see all the anomalies, all what is working perfectly or not. So at this time, you can do your, you can develop your action plan for each transformer. And after, you can do a periodic vibroacoustic tests. You can do it online or offline. So as I told you in the beginning, this is my second part of presentation. In fact, this presentation has been done the January 10th, 2023 and 2023, and by Christian Noël from NB Power. And here the test has been done in Caracat. It was done for a maintenance MR type, and the vibroacoustic and DRM performed before and after maintenance. And this maintenance was performed in T1 transformer. And this transformer is equipped with a Renhausen M3 Delta 5-hand tap changer, which is a specific, which is described here. It's a little complex, I can tell you honestly, for me, because it's like a two mechanism separated. And in general, there are two types of LTC, compartment of box type and in-tank type design. In our case, this LTC is an in-tank design. Although most of our in-tank design are 3 separate phase model, we do have a few delta configuration. And the delta configuration has a cylinder with 2 diverters, and is a regular, and the other is a regular cylinder with a single diverter. Here we can see here you have like a common bar which is which controls the two cylinders. So here it's a vibroacoustic sensor locations. In this case, we installed 2 vibroacoustic sensors, 2 on separate walls near the diverters and located at about 18 inches from the cover. In fact, we use only one, because more you have signals, more complex the analysis. And here, of course, the 2 accelerometers, as you can see here in the graph, give exactly the same information. So it's why we recommend strongly to use only one. And of course, after, when you do your next test, you absolutely need to go to the same spot. Generally, tap operation of this style of tap changer will include the following steps. One of the selector contact is leaving the previous tap position stationary contact, and this moving selector contact is then connected to the next tap stationary contact, and the energy in the diverter energy accumulator is released to switch the load current to the next tap connection. On this graph, we're seeing the sound made by each operations being captured by both vibroacoustic sensors, and also the motor current captured by the EC clamp on CT on the bottom here. And when adding the DRM dynamic resistance measurement information to the previous graph, we can then confirm that when exactly the diverters are switching the current. So here, for example, so you can see exactly that this impact is the one which is important. It helps understand the information provided by the vibroacoustic sensors. And here it's before maintenance. The results shown are from before the maintenance. We are seeing all 3 phases side by side. Here we have the phase A, here on the top right, phase B, and phase C. We are seeing all 3 phases side by side. From this information, we can tell that A phase is not operating in synchronization with B and C phase. And A phase is likely the single diverter, where B and C phases are associated with a double diverter switch that you can see here. These impact, this one is associated here for the first one, and the other are associated for the, well, in fact, the third one. So our test plan calls for testing all the tap transition going up and also back down in this up operation. We're seeing that A phase is operating earlier than B and C. And tap down, but in the down operation, we are not only seeing that A phase is operating slightly later than the other 2 phases. In fact, A phase is operation after the motor current is interrupted. So this could be dangerous, exactly what we have seen like in the asynchronous problems that I have shown in the previous slides. And the timing of this diverter is at the limit where it could possibly not operating during a down operation. So this could be dangerous. This would result in a phase being on a different tap than the other 2 phases. So this graph is now showing the acoustic signatures and DRM information recorded after our maintenance. We are seeing A phase operating now around the same time as B and C, originally about 4 to 4.25 seconds. But the big improvement can be seen on the down operation, where A phase is operating well within the runtime of the motor now. You see, like if you have seen the previous, it was operating at the end of the current, but now it's exactly in correctly aligned. And this aligns with what was seen for BNC. So before maintenance, just to review the before maintenance readings, showing the difference in timing between A phase and the other two phase, you see? So the A phase and B phase. And after maintenance, the after maintenance results now indicate the timing between all three phases is now better adjusted. The selectors and diverters operation are now more in synchronization. I'm not showing the down operation, but the timing was the same as the up operation shown on this side. So summary, Zensol Top 4 can give a good indication of the timing between diverters. When time allows it, can be used before and after maintenance to validate the OLTC is operating properly after intervention. And as we are getting more experience with the information provided by the Top 4, we could use offline acoustic measurements to focus prioritized maintenance on specific units. So, Randy, I think I have finished. Can I stop my share?
No, fine. Yes, thanks very much. Okay, great. Before you began your presentation, I mentioned the failure rate of transformers with tap changers. What is it again?
40 to 50%.
And has there ever been an evaluation of the cost of that?
It's a good question, but in general, when you stop transformer for the tap changer problems, it's just a matter of months, not weeks.
Mm-hmm.
Well, it depends. It's a serious outage.
Right. You know, I mentioned earlier that I had a meeting with the California Department of Water Resources about their transformers. And they mentioned to me that it's very difficult to buy transformers now because there's such a demand. And one of the reasons why there's such a demand in the transformer manufacturing business is because utilities are buying them and storing them. They're not putting them in service. They're storing them in the event they have a failure. They've got a transformer to replace because it takes such a long time to replace a transformer if you have to order one.
Yeah, well, it's exactly what I have seen because, like, I was a few years ago. I have done like a testing, vibroacoustic testing on a. I think it's a handy transformer with a Amar the tap changer, and it was exactly what you said. It was not used. It was just a backup, the transformers in case.
In case, yeah.
And it was brand new, very, and but if they have a problem, what they have to do, just they take this transformer and put it. So this way, it's like a module. Just change a piece of it's something at $5 million, but they use it exactly like a small box, and you put it in place. It takes some few days, and they connect it, and they they're online.
Right. With such a high failure rate of tap changers, is there an alternative? Is there a possibility to have this like an online monitor, constantly monitoring the tap changers?
Well,
or is it only periodically done?
Well, in fact, for me, it's a good question because we have developed exactly for this purpose the OTMX, which is a monitoring online product. So this way, you have a impairment, you have your vibroacoustic, your motor current, and so this way you can compare immediately your events.
Right. Okay.
Yeah. Well, in fact, it's good to have because when you compare the cost of the invention of the instruments and the cost of the high voltage transformers, it's nothing.
Yeah.
And the information is really good information. It's like you have your pacemaker always online with you.
Mm-hmm. You also mentioned about your database. In the beginning of your presentation, you mentioned that you have a database.
Yes.
Do your customers have access to that database? All like, or do they have to download it from you or request their information?
In fact, we provide a part of this database with our software, but
Okay.
after they can, thanks to this part, they can develop their own expertise, or what we do in general. They do like they use this one, and then after they we help them for the first testings, and then after they are enough, they get enough expertise to be able to do this by themselves.
Right.
And because each transformer with the tap changer, it's like, I don't say it's unique, but they have like, we have a 60% common informations. When you have a tap changer, for example, from a specific brand and specific model, you have exactly the same information for this tap changer in another model of transformer. So
The other question I had was whether or not this is instead of buying the test equipment from you, can you provide this like a service?
yes, we provide the service.
Right.
Yeah.
Okay.
In general, what they do, the people, what they do, they buy the service just to be familiar, to how do you say, to be to learn what is this, and then after they're interested to buy the instrument, or to do their monitoring with our OTMX.
Right. Okay. Great.